Okay, so we talked about equilibrium a couple of times this quarter. We talked about physical equilibrium, both in the case of colligative properties and in talking about vapor pressure, and I think talking about solubilities. There's lots of things we've talked about physical equilibrium. Now I'm going to talk about chemical equilibrium, but you guys should be fairly familiar with the idea of equilibrium. So, remember, equilibrium is that state that we've talked about where two opposite processes are happening at the same rate. This is why I talked about rate before. They're happening at the same rate, so there's no net change, but this reaction is still happening, or whatever is still happening. So, until now, we have assumed that a reaction goes until one or more of the reactants is completely gone. So, like, we have H2 plus O2, and I'm going to balance it here in a second, don't worry. Right? This reaction, we assume that we have been assuming this reaction will go forward until either all of the hydrogen or all of the oxygen is gone, one or the other. This is a fine assumption. This is totally true, assuming that product concentrations aren't allowed to build up. Assuming that we just keep removing the product from the reaction as it's created, this is a fine assumption. But something happens if we let the products build up. And you guys might be able to piece together what we've talked about equilibrium already and piece together where I'm going with this. You know, we've always considered reactions as one way. But what could happen, depending on the reaction, products can actually react with each other to go back to the reactant. So the idea is that we now are need to think about the reactions as being reversible. The reaction can actually go back the other way if there's enough product to allow it. So if I have just a generic reaction of A plus B produces C plus D, right? We also have to consider the fact that any buildup of product, D and C, might react and go back to A and B. Because if you think about this reaction diagram as we've been looking at it, right, it doesn't really matter, right? So this reaction, as it's written, is exothermic, right? Products are lower in energy than reactants. But you can also have an endothermic reaction back the other way. It could totally happen. So there's nothing saying that the reverse reaction can't happen, and in fact it does. If we let the products build up, this reaction indeed will happen. So, in reactions where we see this, we actually often write a double arrow to imply that the reaction can happen both ways. So, actually, let me go to a concrete example here. We'll talk about this and we'll see where equilibrium comes into play. So, N2O4 breaks down into, so N2O4 is a colorless gas. It breaks down into NO2, which is a dark brown gas. So this is the reaction. What happens is, if I let this reaction happen, the brown color increases to a certain intensity and then stops. And no, it's not because we run out of N2O4. At this point where the brown color stops increasing in intensity, we still actually do have N2O4 in the reaction. Or in the container. So here's sort of an example of what's happening. It gets darker, darker, darker brown and stays there. So let's look at this. Let's kind of pull this apart and look at what's happening. So as the reaction proceeds, so initially, so we go back here, initially, and so what these are, this is concentration. Initially, there's no NO2. In fact, maybe this is another way to do this. There's no NO2 to start with. There's just N2O4. So what happens is, initially, there's no NO2, no reverse reaction can happen, right? The N2O4 is just going to break down into NO2. So what happens is the concentration of the reactants goes down, right? The concentration of the reactants goes down, and the concentration of the product starts to increase, which is what we see in this chart here, right? So the N2O4, we lose N2O4, we lose it, it starts breaking down. The NO2, we start getting more and more and more, which is this increase in the brown color. Okay. Let's talk about it in terms of rate, however. So I'm going to use So I'm going to draw this graph. I'm going to do over time of this reaction. And I'm going to say, I'm going to use blue to indicate the forward reaction. And then we're going to talk about this reverse reaction here. So NO2 plus NO2 breaking in, or combining back to make N2O4. And I'm going to use the red line to talk about the reverse reaction. So I'm going to talk about rate. This is a different graph than the one that's on the previous page. So what we're going to do is we're going to talk about it in terms of rate. So initially, the rate of the reverse reaction has to be 0 because there's no NO2 to react at first. But there is N2O4, right? Now, as this reacts, so the reaction rate of the forward, so forward, and the reverse, as the rate, when the rate of the forward is higher than the rate of the reverse, what's happening is we're building up product and losing reactant from this perspective. So, as the concentration of N2O4 drops, what happens to the rate of the forward reaction? Well, it's going to go down. It's going to slow down, right? Well, but by the same token, once we start producing NO2 and there's more and more and more and more of it, that rate starts going up, up. Eventually, the difference turns into this. So what happens is they eventually reach the point where they're both happening at the same rate. I'm having trouble drawing the lines right on top of each other, but there it is. The idea is that what happens is you reach a point where the forward reaction and the reverse reaction are happening at exactly the same rate. This will always eventually occur, and this is called chemical equilibrium. So this is where the concentrations of all the reactants in the products remain constant with time, and it's where the forward and reverse reactions occur simultaneously at the same rate. So this always happens, right? This is always going to happen. Any reaction, if we let sit there, will reach chemical equilibrium. And so, at the molecular level, both the forward and reverse reactions are occurring. They are happening, but at the same rate. It's dynamic, but on the macroscopic level, from your perspective or my perspective, it doesn't appear to be changing at all. It just seems to be constant.